Hi everyone. Today we look at the paper Learning to Compress Prompts with GIST tokens. So this paper focuses on how you can reduce the number of prompt tokens and learn a bunch of tokens called as GIST tokens so as to improve the computational efficiency in the context window. So usually your prompts are in the context window, and if you have long prompts, they take up a lot of space in the context window. And since attention is quadratic in the sequence length, if you have longer sequences, you're basically going to increase your inference time. So in order to avoid that, they propose using these GIST tokens to reduce the number of tokens in the context window. So, to recall, prompting basically allows the language model to do multiple tasks, right? So you can switch between tasks by switching the prompt. So essentially, you're trying to produce an output Y based on the description of the task as well as the input X. We'll call the description of the task T, right? So you could solve a math equation, you could summarize an article, you could translate to French, all using the same language model by just switching the prompt, which is in the context window, right? And now compare prompting with fine tuning and distillation. So in this paper, they're trying to reduce the number of prompt tokens, and fine tuning and distillation achieve precisely that. Because you fine tune or you distill for a particular task, you need not really specify any of the prompts relating to that particular task, right? So you're going to have one model just aiming at translation, another model aiming at summarization, and a third model aiming at solving math equations. The drawback of this is you're going to have weights which are different for each task. Gisting is sort of in between, where you're not going to completely do away with the prompts, but rather you're going to have a couple of tokens called as gist tokens. Here they are denoted as G1 and G2. And now they are going to take the place of the prompts, right? But you also don't want to fine tune for a particular task or a data set. So you want to retain the ability of the language model to handle multiple tasks. But now you are just going to inference using these gist tokens, right? So thereby you're basically saving the number of tokens which are there in your prompt, and essentially you're going to make inference faster because now your sequence length gets reduced and attention basically, which is quadratic in the sequence length, will be computed faster. So the way they go about doing these, learning these new tokens or the GIST tokens is shown here. They play with the different attention masks, and that's how they accomplish it. So they try the experiments on two different types of transformer models, decoder only and encoder decoder, right? So to recall the problem again, you have the prompt T, and you have a couple of GIST tokens. They play with the number of the GIST tokens, and then you have your input X or the query, right? And the idea is to basically, for the input to just use the GIST tokens at inference time, but then you have to learn these GIST tokens, right? So you learn this by instruction fine tuning, right? And during instruction fine tuning, you want the language model itself to learn how to produce these GIST tokens based on the prompt, right? And one thing which they do here is, now you can recall there's something similar called prefix tuning, where they have a bunch of prefix tokens which they learn per task. But the key difference here is these GIST tokens are going to be generic across different tasks, right? So let's look at the decoder only model and see how they accomplish that here. So in the decoder only model, this is autoregressive, right? So when you look at the attention, a token can only attend to its past tokens. So let's say you have the GIST token G2, it can only attend, GIST token G2 can only attend to translate French and G1, and that's what's shown here. G2 attends to translate French, G1, and also itself, right? So now what they want to accomplish is pretty simple. They want the input to basically only rely on the gist tokens, right? So the inputs, the cat, should only attend to the gist tokens and not to the prompts, right? So they mask off the prompts but attend to the gist tokens. The same thing, and the input as well, right? The same thing with the as well. You mask off the prompts and you. But the gist tokens sort of learn how to compress the prompt by paying attention to the prompt. So you have G1 and G2 actually paying attention to the prompt T or the task description, right? So that's how you accomplish learning of the gist tokens during instruction fine-tuning phase. When you look at encoder decoder models, now this is a little different. Now, if you recall in the encoder model, you have bidirectional attention. Basically, what that means is any token can pay attention to any token either before it or after it. So that is a bidirectional attention. But again, we need to make sure that the constraints of the task are reflected here. And we said that we want the input X to only pay attention to the gist tokens, right? So we are restricting attention from the input to the prompt tokens. The gist tokens, on the other hand, can pay attention to the prompt tokens, but you don't want the gist token to pay attention to the input. And this is because you don't want any of the representations of the input to basically reflect into the gist tokens. The gist tokens are just there to compress the prompts, right? So this is the modification you would do for attention on the encoder side. On the decoder side, it's very similar to the cross attention is going to be very similar to the autoregressive decoder mask, where this is the output. You just want the output to pay attention to the input, just the input, which is the cat, and also the gist tokens. You don't want them to pay attention to the prompt tokens. So by doing this kind of a masking, which they call as gist masking, you essentially force the language model to learn these gist tokens. And since you're instruction fine tuning on a variety of different tasks, right? So they have some details. They call their data set as Alpaca Plus, which has a bunch of different tasks, inputs and outputs, and a bunch of different tasks. They combine self-instruct and Alpaca dataset. So they're going to learn generic representations of these gist tokens. So next, they run their experiments, and then to evaluate these models, they evaluate on prompts which were, so again, the prompts as such, you could have seen that during the instruction training, but the inputs could be new, right? So those are called the seen prompts. And in the unseen prompts, you have instructions or tasks also which are not seen by the model during training. They are brand new. And in the human split also, you have tasks which probably are written by humans, right? Which likely they wouldn't have encountered during training. So these basically the unseen and the human tasks, they kind of tell you how the model performs for out of distribution tasks, right? And then they compare their model with two baselines, a positive control baseline. This is if you had the prompt and you had one gist token and you had the input, but you don't restrict the attention mask at all. As in the input can pay attention to the prompt as well as to the gist token, right? So that's the positive control. This is almost like not having the gist token and just learning from the prompt. The negative control is when you remove any of the prompt tokens and you only have the input. This is like the model has to figure out what has to be done, right? A model which is trained like this, right? So here you're also obviously going to provide the output Y, right, for this. So here the model is just going to look at for the negative control, it's going to look at the input and the output and figure out what it has to do. So that's the lower bound of how bad the model can go. And in terms of evaluation, they are looking at the Rouge score of the generation, which basically looks at the exact lexical overlap between what's generated and what the expected output is. And they also have ChatGPT evaluation. So basically, they're giving two different inputs to ChatGPT and asking its preference of one over the other, right? Um, and here you're basically always comparing your model with the positive control. So you have the compressed version where you just have a couple of gist tokens for the prompt, and you have the non-compressed version, which is a positive control, which has the prompt tokens as well. And you're asking ChatGPT which one it prefers. So let's look at the results. They performed the experiments on Llama 7 billion. This is a decoder only model, and the FLAN T5, which is the encoder decoder with the encoder decoder masking you've seen before. And you can see that with the GIST token, the model performs as well as if it was trained using the entire prompt token, right? So the performance is almost closer to that compared to the negative, where it didn't have any prompts at all. And this is reflected both in terms of Llama as well as in terms of Lantify. And then they vary the number of GIST tokens, right? You can have, we said they'll have variable number of GIST tokens. So these only need to be added to the embedding matrix during the supervised fine tuning phase, and they will be learned, right? So they have 1 to 10 GIST tokens, and some of the results are interesting. So what they find is just having one GIST token is good enough, right? You can almost get a Rouge score as similar to the without having any GIST tokens and having prompts, right? And having a lot of GIST tokens, like 10 of them, sometimes seems to hurt the performance. So having lower number is better. And this is on the scene prompts, right? Maybe it sort of overfits at this point. And then you have the unseen and the human. These are sort of like out of distribution. So you can see that having more number of GIST tokens helps in this way in the unseen case, whereas in the human case it sort of plateaus, so it doesn't really matter. And the same, and then you look at the win rate against ChatGPT, and you see that it's almost like 50% of the time the model prefers the GIST model versus the positive control model. And you can see that across the board on unseen prompts as well. But when you look at the human prompts, it seems like if you use too many GIST tokens, ChatGPT is not liking your GIST model compared to the positive control model where it gets the prompts. And you see a similar pattern here in terms of LAN-T5 as well. And then they actually look at the efficiency of these GIST models, right? They compare it with no caching, where you have the entire prompt, right? This is the no caching model, where you just have the prompt and then you are paying attention to the entire prompt on the fly during inference. And then you have the instruction caching, where so since the prompt is repetitive, you can basically just cache the keys and values, right, of the prompt. You don't have to compute it every single time during inference, right? And then they also have gist caching, which is instead of computing the keys and values for the prompt, they are now doing it for the gist tokens, right? They just cache the activations for those. And then you can see they measure the wall time, which is the end to the time taken to execute something, right, from beginning to end, and also the number of floating point operations which are done. And you can see that when you have these GIST models, they basically reduce the wall time as well as the number of operations, the number of floating point operations significantly. And caching instructions also sort of does this, right? But the drawback there is your caching instructions for a lot of different tokens versus so the memory efficiency is not great when you're caching instructions for the entire prompt. So that way, just token sort of wins in that department, right? And then they look at the exact match date, right? This is when your GIST model produces the same strings as the positive control model, right? And they find that around 45% of the time for scene prompts, or around 40% you can see based on the model you're choosing, it produces the same exact string as the positive control model. For the unseen prompts, this number sort of reduces, and for the human prompts, it doesn't. Only 10% of the time, around 10% of the time, you produce the same prompts as the positive control model. So the main takeaway is here it's introducing a different framework called gisting, where you can compress the number of tokens in your prompt. And this is computationally more efficient and more efficient memory-wise. And it gives comparable performance if you've trained on tasks which would be used at inference time, like seen before. So yeah, the main contribution is this gisting framework.